All right. Thank you all for tearing yourselves away from lunch in the courtyard conversations. And so today I'm going to be telling you about some of the experiments that we're building up in my lab to look at new kinds of waveguide QED systems using superconducting qubits and superconducting circuits. And so I want to start by introducing our building blocks, because I think this is a relatively AMO audience, and we have some tricks up our sleeve that are very hardware dependent. And so half of our toolkit is superconducting microwave cavities. And the kind that I'm going to focus on today is the coplanar waveguide cavity. And so this is the basic structure that we make things out of. You should think of it as a two-dimensional version of a coaxial cable where there's a center pin and two ground planes on either side, and that guides microwave photons along the chip. However, if you cut the center pin, then that creates a very strong reflection where you've broken your coax geometry, and so you get a very nice guided mode of microwave photons that sails from one end to the other and bounces back. And so this is our version of the Fabry-Perot cavity. In practice, they look more like this because we need to deal with our about 8 millimeter wavelength, and so for compactness, we tend to fabricate them actually with meanders like this. And the fact that we can do that is actually really key to the devices and some of the places that we want to go. If you don't like thinking about hardware, it's a harmonic oscillator, charge and flux instead of position and momentum, but basically this is our favorite harmonic oscillator. The other half of the toolkit is, of course, superconducting qubits, and so in my talk today, I'm only going to be talking about transmons, which are the most common and the simplest kind. And so this is the circuit diagram for a transmon. So it's a capacitor in parallel with some Josephson junctions. And you can really think of this as an anharmonic oscillator. And so instead of charge squared, flux squared, the Josephson junction gives you a cosine phi. And so you can think of the transmon as being a particle in a cosinusoidal well, and it's the anharmonicity of the cosine that makes the levels not equally spaced, but this anharmonicity is relatively small. And so we're mostly going to focus on the lowest two levels here, but I will show you some data later on where the second level makes appearances. And so what we can, the other thing that's really important is I've shown here the version of a transmon with a squid in it, and what that means is that we can tune the effective EJ by applying a flux. And so this is a very, very frequency-dependent atom. We can tune it from probably around 1 gigahertz up to about 10 gigahertz, the ones that we're using in the device that I'll show. And so this is what our transmons today actually look like. So the yellow and the blue are actually the capacitor, and this red portion here is the squid loop with the Josephson junctions. And this is showing actually this transmon embedded inside one of the coplanar waveguide cavities. This is the center pin and with the ground plane on the outside. And so what we have is just an artificial version of the Jaynes-Cummings model. It looks very, very similar to the Hamiltonian that you would expect for atomic QED. The difference is really just in the energy scales. We're talking about 5 or 10 gigahertz cavities and 5 or 10 gigahertz qubits, and we can have coupling strengths easily of 100 megahertz or so. And so this is very nice, strong coupling QED, essentially for free from the microwave cavity and the Josephson junction. And it's so strong that we can really start to play around with multi-mode structures and still have very strong cooperativities. And so what I like to play around with is lattices. And so in my world, this is what a lattice looks like. This is a device that was fabricated in the Hauck lab around 2012. So we've now zoomed out. So each one of these squiggly lines is a coplanar waveguide resonator. You can no longer actually resolve the center pins and the gaps. And they meet at these little black dots. And so what's going on there? So at this junction region, you have the center pins of 3 cavities converging on the same place, and you have some extra capacitance here, which allows a photon rattling around in one of these cavities to hop into the other one. And so you can think of this as a capacitively coupled resonator network, and I like to just abstract this away as a tight binding solid for microwave photons, where the on-site energy comes from the resonant frequency and the hopping comes from the capacitance in this 3-way pizza pie coupler. One comment for folks who've played around with band structures, the sign of the hopping in these systems is anomalous. So your general physics intuition that long wavelength things are at low energy and high wavelength things, and that short wavelength things are at high energy is backwards. These band structures are going to be upside down. The long wavelength stuff is at high energy and the rapidly oscillating things are at low energy. So there's just a global minus sign compared to what you're probably used to in other systems. In addition to this sort of minus sign, there are really two fundamental properties of these resonators that make for interesting waveguide QED that you can do. And so the first is that this site is made out of a waveguide. And that means that the shape of it is very flexible. So if you're a photon in this resonator, then you fly down to the end, bounce back. And so the frequency is really just set by the total length. It doesn't care about having meanders. So this shape and that shape can have entirely the same frequency. And the other thing that's really nice is that unlike an atom where the potential and the orbital really determine the hopping, in this case, the hopping is just determined by how big of a capacitor we plonked here at the end. And so you can have really separate control over the coupling, the frequency, and the shape. And so that means that conventional crystallography doesn't limit what you can do here. If you need to fit something in a slightly smaller area, you can change the shape. If you need to bridge a larger distance, you can stretch it out. And so that's going to allow us to go to lattices that would not otherwise be possible. The other thing that's important to remember about these kinds of lattices is that our lattice site is not a point-like object, it is a line-like object. And so if you look at this photo, then the lattice describing how the photons move is actually a Kagome lattice, right? The resonators are the sites, and you have a hopping matrix element if two resonators share an endpoint. And so all of the hardware that I'm going to draw is going to sort of look like a honeycomb, but it's going to make Kagome-like lattices, which are a mathematical object called a line graph. And it turns out that basically every single one of these is guaranteed to exhibit flat bands. So we have very flexible layout and connectivity, and we have a massive predilection for making flat bands that comes from using CPWs as our lattice site. And so what we want to do here is take this flexibility in controlling the photons and combine it with the qubits. And so if you put two qubits in a cavity, I think we've seen this many times now, the sort of simplest kind of interaction that you can get is a photon-mediated exchange. One qubit de-excites, it emits a photon, and the other one absorbs. And if you do this in a single-mode cavity, this is an infinite range all-to-all interaction. But if you have a multi-mode system, then you have a sum over all of the different modes, and the different modes have different spatial structure. And so this sum creates an interference, which gives your interaction some locality and spatial structure. And this is the limit that we want to get into. And so in a 1D chain, this has the well-known result of giving you an exponentially localized interaction. But because we have CPWs, we can do crazier things than that. And so, for example, you can use the flexibility of the shape of the resonator to make a lattice where the photons feel like they're moving in a negatively curved space. And if you do this and embed qubits in it, then you should get a hyperbolically connected spin model as well. And so this is where we're hoping to go in the long term. We are not there yet. And the other thing is that we have all of these flat bands. And these flat bands are full of highly oscillatory modes and lots of triangular plaquettes. And so again, there's a very strong tendency to try to make short-range frustrated magnets. And so what we've been doing in my lab is trying to take this from a theory slide to an experiment slide. And so what I want to talk about is the device that we have made really as a prototype, because previously there have been resonator-only devices of this kind. And there have been qubits in devices with much simpler lattices. And so what we want to do is we want to combine an interesting lattice with qubits and go through all of the work and the engineering to make this all work in the lab. And we've had to develop a lot of new measurement techniques to actually see what's going on in these lattices. And so this is the lattice that we chose to make. So the hardware is connected like this. The actual photon lattice is this sort of ruby lattice chain. And the reason that we selected this is it was kind of the perfect playground to have all of the possible dispersion relations that we could get in 1D. So we have flat bands, we have quadratic bands, we have linear band crossings. It sort of has all of the things that you could ask for in a relatively simple 1D lattice so that we can make a nice thing with good bulk to boundary ratio. And so this is the design for the device that we've made. And so the lattice itself winds on the 2D chip like an S-curve, like so. And so in the center here, I've highlighted one unit cell. It has 6 resonators. And what we've done is we've embedded in this lattice 3 qubits, which are shown, which are at these highlighted locations, each of which has an on-chip flux bias line that gives us independent frequency control over all 3 of the qubits. In addition to the qubits, you might notice the little purple caterpillars that are crawling everywhere over this device. And what this is that the transmon itself is a relatively large perturbation on the resonator. You have to carve out a chunk of the ground plane and then put in these extra capacitor paddles. And so to keep that from detuning these 3 sites here that actually have the qubits in them, what we've done is we've written the capacitor portion of the transmon in every resonator, but only added the Josephson junction in these 3 locations. And so that keeps the disorder relatively low while giving us these 3 tunable emitters inside the lattice that we can bring into contact with the various energy bands. So that's the CAD. And this is this transmon again that's embedded right there. So in practice, this is what it looks like. So this is a photograph of the chip at the photolithography stage. And so what you're looking at here is a tantalum film. That's the black that you can see. And everywhere that's white, you are seeing through sometimes about a 10 micron gap in the tantalum film to a white, tech white behind. Once you actually package it up, it looks a lot messier. So this is now entirely wire bonds that you're looking at. Anybody that has worked with a wire bonder knows the amount of patience involved with sitting and doing this many of them. But we've cooled this down during March meeting in proud superconducting circuits tradition. And so we cooled it down, and this is the kind of thing that we see. And so let me walk you through this a little bit, because we're going to be looking at data like this quite a bit. And so what we are doing here is we are doing transmission spectroscopy, sending a microwave photon in coherent state in on one side and looking at how much we get out on the other side. And so we see a series of peaks which should correspond to the normal modes of this lattice. And in addition, because the qubit is frequency tunable, we can just move the qubit through the lattice. And as it goes through, it leaves a trail of avoided crossings in its wake. So this is one of the qubits doing a complete transit. The other thing about the transmon actually is that the frequency is periodic. And so this is a shot of one of the qubits going down to its minimum frequency and back up again, leaving these avoided crossings here. And so what this is showing is that we have live qubits in this lattice, and that the interaction strengths with the photon modes are comparable to the mode spacing. So we have a sort of multi-mode strong coupling system. And so that got us very excited, but we really wanted to make sure that we'd made the device we promised to make. And so we can't just measure the band structure directly. We don't have momentum resolution. We only have energy resolution. And so we've spent a lot of our time learning the right way to find these bands and measure things. And so another sort of odd thing about coplanar waveguide resonators is that the lowest frequency excitation is actually asymmetric. It has positive voltage on one side of the resonator and a negative voltage on the other, and that gives you a sort of P-wave type binding model. It actually has this band structure rather than the one that I showed you before. And so if we now look at this transmission data, this is a guide to the eye of where we think the bare qubit is. And so you can see that there's 2 regions, one over here and one over here, where there's a series of avoided crossings. And so at first glance, this seems to correspond to a narrower set of bands down here and a wider set of bands, but there's also some weirdnesses, right? So some of these modes are peaks, some of them are phonoresonances, and this region here in the middle that's supposed to be the band gap is basically as bright as some of these lattice modes over here. And so at first this threw us off, and what's going on here is this is, by microwave standards, a really large chip. It's 25 by 25 millimeters, and so that means that there's transmission through the device. There's also transmission around the device. And so what we're looking at here is actually the interference between some leakage that's going around and the actual lattice modes, and that's leading to this extra transmission here and these phono line shapes. And what we've figured out is actually there's a much better way to take this data and to find the bands. And that's to use the fact that the qubit itself is nonlinear. And so what we've done is we generalize a two-tone spectroscopy method that's normally used for reading out qubits. And so the basic idea here is that you put a weak monitor tone on a cavity resonance, and then you scan a stronger tone and you try to change the state of your qubit. And because the qubit's nonlinear, if you manage to excite it, it moves the cavity mode. This is the standard readout mechanism for qubits, and there it's, single excitation resolve, but this works here between the cavity modes because they inherit a nonlinearity from the qubit. And so that's what this data is shown here, is we're monitoring one of the cavity modes, one of these normal mode resonances, and then scanning a strong probe tone. And if it hits a resonance, it populates the cavity and it shifts the monitor mode out from under the pump, and that's where you get these dips. The darker the color, the harder we're driving. And this measurement is using the qubit-mediated nonlinearity, and so it doesn't care about big delocalized modes that don't couple to anything. And so now we get a hard band gap, a set of modes, hard band gap. And it goes, and it also shows us modes that were otherwise sort of hiding because they couple relatively poorly. So there's an extra teeny little mode up there that you can almost see in transmission, but it's definitively there in the nonlinear spectroscopy. And now we can make a much nicer comparison to the expected density of states. And so this is a numerically computed density of states for those bands. These dark lines here are the flat bands, and the lighter blue is the dispersive bands. And this is a pretty nice match. So we're very happy with this. So then we go and we start to look at the second set of modes. So this is the second harmonic now at 10 gigahertz. And that's the one that has this band structure with this very highly unique gapped flat band that originally got us looking into this. And now we do transmission, and this is a lot messier. It's higher frequency, there's more parasitic modes in the package, and now we have a mystery, which is that theory says there should be 3 sets of bands, and I only see this one central region of avoided crossings. And so we were worried for a little bit, but this is where the nonlinear spectroscopy really comes golden, because that's what the nonlinear spectroscopy looks like. And so it says there's more modes down here. This is where the flat band is supposed to be, and there's more modes up here. And if you zoom in here and you look very carefully, you can actually see these modes clearly in the transmission, but it's hard on the same scale. And so this we can now compare with the expected density of states. The match is not as good as at the half-wave modes, but it's much better. And so even though we can't see these gap flat bands here in transmission, the nonlinear spectroscopy, which we call mode-mode spectroscopy, shows very clearly that there's a cluster of narrow nonlinear modes living at this frequency. And so this convinces us by looking at the photon modes that we have the lattice structure we wanted to make. But so far we've only seen the qubit as a guide to the eye. These are drawn in Keynote, just to roughly show where these are, and we see it only implicitly in the avoided crossings that it leaves behind. But what we can do is use exactly this two-tone spectroscopy method to find the qubit. And so it's the same kind of thing that we do to find the modes. We just go with much lower power. We don't blast it nearly as hard. And so now I've added 2 more patches of data to this plot. So this one here and this one here. And so these are this two-tone spectroscopy data. So we're monitoring one of the cavity modes and then using a strong drive to try to flip the qubit. And so these 2 curves right here are actually showing qubit-like dress states that live in the gap. So the bare qubit transition is doing something like this, and this is the actual two dress states that we have. And so what you can see down here is that the qubit is avoided crossing with something here, even though the first modes that are visible in transmission are up there. And so we have an extra confirmation that this qubit is seeing that flat band, and when it gets high enough, we get a second photonic bound state emerging in this upper band gap here. Okay, so we've seen the qubit near the photon modes, but we started out wanting to actually observe the kinds of unusual photon-mediated qubit-qubit interactions that we could get from these unusual bands. And so for that, we need to go further into the band gaps, because in this regime, we really got a lot of hybridization between the qubits and the photons. And so we're getting nonlinearity, but we're also inheriting the lifetime of the photons. And so what we can do is we can now not look in here, but we can start to look down here, well into the band gap below the modes. And we use the independent flux bias control of the qubits to tune the qubits across each other. And so this is two-tone spectroscopy data showing two of our qubits, one held fixed and the other one ramping through. And if we go sort of well below the modes, this avoided crossing is very small, but as we get closer and closer to the bottom of the band edge, we open up a larger and larger interaction. We can also do this up near the full wave modes, and so now we're looking in this region. And we also get very clean avoided crossings there. And now we've picked up another feature, which mystified us for a little bit, but this is actually the two-photon transition to the doubly excited state, which is hiding here in the middle. Okay, so basically what I've wanted to show here is that we've been able to make this device verify that it has these unconventional bands, and that we have the ability to tune these qubits around and measure them, even though we have sort of weird normal modes that we have to use for readout, and very high frequencies, and that we can get around some of these unfortunate sort of transmission artifacts to get very clean measurements of the qubit-qubit interactions. All right, so what are we doing next? So we've been trying to get better at measuring what our modes actually are and understanding the nonlinearity that the photon modes actually inherit from the qubits. And so one of the questions that you might ask when looking at this data is, what is G? Right? We've sort of verified that we have the hopping that we wanted and the connectivity, but it's very hard to read G off of this plot because the avoided crossings are so large, these modes are actually banging into one another. So we can't get G from a vacuum Rabi splitting because the modes are all talking to each other. And we can't get it from a dispersive shift because the dispersive shift is collective. And so what we've started to look at is try to use the Kerr effect instead. So this is the same kind of measurement as the mode-mode spectroscopy, but what we were doing there is just wailing on it as hard as we could. Blast the thing. Is there a mode here? Is there not? And so what we're doing now is going at much lower power, trying to get information out of the size of this shift. And so if you have two modes that are coupled to a qubit, then sort of at lowest order, they inherit this fourth order Kerr nonlinearity. That has a very simple form for a two-level system within the rotating wave approximation. So GA squared, GB squared, and some detuning dependence. The actual form for a transmon is like the full width of this slide. Nobody wants to look at it, but the key is that it has the same GA squared, GB squared dependence, and there's just some complicated function that depends on the detuning and the anharmonicity. And so if we can measure the size of the Kerr shift per photon, and we know these detunings from doing spectroscopy, we can extract in situ Gs for the individual modes of the lattice. And we do that by looking at the frequency shift when we drive one mode. And so this is the measurement that we're doing. We pick two modes of the lattice. We have the qubit down here below, and this is just going to be the mediator of the interaction. We're not going to measure it directly. Okay, perfect. I timed this well. And so what we do is we're going to drive one mode really hard and weakly monitor the second mode. And so we get data like this. As we increase the drive power, the monitor mode shifts over. And this is preliminary data showing the detuning dependence. And so we have a measurement of the Kerr shift, but there's two problems with this measurement in terms of measuring in situ Gs. It depends on two Gs. It depends on the two modes that we chose. And perhaps the much bigger problem is this is Kerr shift per milliwatt of power outside of the fridge. This is not Kerr shift per photon. And that's actually a very hard calibration to do. We've got like 80 decibels of attenuation on the input, and there's a mode matching factor. And so what we actually do here is we compare a Kerr shift measurement and a Stark shift measurement, because those both go as G squared and the photon number, and we use that to remove the insertion loss. And so preliminarily for this particular mode, we find an in situ G measurement of about 9 megahertz. So we're working on ironing out the kinks and making sure there's no errors in here, but we're starting to get these measurements to work. The other thing that we unexpectedly saw when we were looking at this is that we don't just see Kerr processes going on here. We think we've now seen a form of resonant wave mixing. And so the measurement that we're doing is we're weakly monitoring one of the cavity modes, or the normal modes of the lattice, and we're scanning a strong drive looking for the qubit. And what's unusual in this device is there's multiple monitor modes to choose from. And so as we do this scan, this is 4 examples that were taken last week, and we see the normal things that you expect to see. So this is the 0 to 1 qubit transition here. This is a 2-photon transition to the second excited state, but then there are these 4 guys. They're moving with the monitor mode, and they exactly move by however much we change the monitor frequency. So these guys haunted us for months. They were corrupting all of our measurements because they were running around. But what we think these actually are is a 4-wave mixing type process where you absorb a monitor photon and a drive photon, you excite the qubit, and you produce a 4th photon. And so if we look at some other mode, you get a 4th photon. And so if we look as a function of flux bias, we can see that this extra peak tracks the qubit frequency, and we can also try to infer the mode that it comes out at. And so this is the nonlinear mode spectroscopy shifted down, and it appears to be coming from a particular mode which is near one of the flat bands. So somewhere we would expect to find the mode with the single largest G. This is, again, very preliminary data, but it looks like these are actually systematically popping out near our flat bands. So that's cool. And so then I probably have like 2 minutes left. Okay. So now for a completely different topic in the last 2 minutes, I just wanted to flash up a teaser trailer for another project that we've had. And so here we've been looking at a very basic Floquet model of a spin in a rotating magnetic field coupled to the qubit. And we make this by combining a Rabi rate and a flux bias. And what I really want to show you is the effect of the cavity on this model. So you have the spin in the magnetic field. It's slowly rotating. We're in the adiabatic limit. And so what you expect to see here is you have 2 eigenstates, one where the qubit is aligned to the field and one where it's anti-aligned to the field, and the qubit should adiabatically follow. And so what we have plotted here in blue and orange are data taken where we start initially aligned or initially anti-aligned, and we rotate the field. And so at far detuning, when you're not near the cavity, you get an oscillation up and down, and the 2 configurations are exactly 180 degrees out of phase. But T1 and T2 processes in the qubit eventually spoil this, and so it decays away into a mixed state. But if you go near the cavity, so not qubit on resonance with the cavity, but the Zeeman shift, bringing one of these 2 states within G of the cavity, something qualitatively different happens. They start out of phase, but they end in phase. So you have the same amplitude and the same phase for both. And this initially aligned thing decays away and then comes back into phase with the anti-aligned. And if you go even closer to resonance, you get a much more dramatic effect. And so these are oscillations going on for 100 microseconds, and you see that both initial states converge to the same thing. And I've put, for comparison, a T1 curve of this qubit. So this is doing this oscillation happily long, long past the lifetime of the qubit. And so what we've come to understand, and is in this recent arXiv paper, is that this is a version of optical pumping for flow K states. And so the cavity is causing one of these two states to be lossy, the orange one. And so then even though you started aligned to the field, the cavity pumps it into the other one. And then if there's a T1 process that takes you out of that, the cavity pumps it right back again. And so these are fairly high contrast oscillations going on, from our point of view, effectively forever. We got bored at 200 microseconds and stopped. But that this really does seem to work remarkably well. And so that's, if I had a 45-minute talk, there'd be more than one slide. But given that I don't, I would like to just wrap up. And hopefully I have convinced you that you can do a lot of fun multi-mode QED with these superconducting circuit systems, and that we have sort of unique access to unconventional photon dispersion relations and bands, and we have also the ability to flux tune the qubits wherever we want into these modes. And so we have a lot of selectability and some amount of in situ tunability, and that we've started to look at photon-mediated qubit-qubit interactions, multi-photon processes, and this cavity-stabilized flow K state was actually a big surprise to us. We did it by accident and then had to figure out what we had done. And so with that, I should, of course, thank everyone that made this possible, to all of the funding agencies that have supported this work. So the students highlighted in red are the ones that have worked on this current generation of the Lattice device, or have done theory results looking at the wave mixing and the Kerr. And then the students highlighted in purple are the ones that worked on the cavity-stabilized flow K project, which is a collaboration with Alicia Chandran at BU. Okay, thank you.
Thank you so much, Alicia. Questions? Okay, if there is none for now, I will start. So I have a question about the limit of this kind of toy model when you describe your lattice and the qubits coupled to it. So I guess two questions. So the first one is, at some point, if these bands are really flat, this retardation will start matter. So this kind of integrating out the band to get like this spin-spin coupling would break down. So do you see any instance of this? And the second thing is, with respect to the level structure of the transmon, right? This is an anharmonic oscillator. So do you ever see like these kind of like 2 zero states popping up?
We see them, and it has been measured before in other devices. The second excited of the transmon also will have a photon-mediated avoided crossing. We thought we saw it many times, and it was in fact the wave mixing resonances, and so that's how we got onto that. But mostly we don't see much effect of the higher order states of the transmon. The thing that we've actually started to really see is that the tight binding approximation is not good enough. Mm-hmm. So we have hoppings of about 40 or 80 megahertz and a frequency of 5 to 10 gigahertz. And that's just large enough that we're starting to see terms that were neglected by the tight binding. So some counter-rotating terms and some intraband terms. And so we're working on this with Alexei Gorshkov, but it actually looks like our flat bands are shifted compared to the band edges of the dispersive bands. And a more exact circuit calculation seems to back this up. And so I think that's more what we've seen, that these band edges have moved a little bit.
Thank you. Yeah, Igor?
Thanks a lot. I really appreciate the last part that you showed. This reminded me of, you have 2 classical oscillators that have like dissipation friction between them, and so due to this friction, they will synchronize with each other. And what's interesting in that problem is that if you increase dissipation, actually you will actually increase the lifetime. So if you have like 0 dissipation, they will like never synchronize, and then you increase dissipation, they will decay down. So is there an equivalent here? If you change dissipation, will your qubit actually decay faster if you decrease dissipation?
I think that what we actually see here, everything that we've seen is much more in keeping with a sort of competing rates sort of issue. That the qubit is going up and down and up and down and up and down. And so what that means is that, say, spontaneous emission in the qubit does not just take you to the ground state, it can take you to the excited state. And so the qubit decoherence processes are giving you heating. And that's constantly trying to take you out of whatever state you're in into the other one and just scramble everything up. But the photon is not being turned upside down and driven, and so the photon decay still goes downward. And so we can't tune anything in our device, but Alicia has done a lot of numerics, and what you see there is that if you up the dissipation, you will get to this steady state faster, and the contrast in the steady state will go up.
Exactly.
And so this finite contrast really should be thought of as you spend X fraction of your time jumped to the other state before you pump back. And this contrast, we have better measurements using adiabatic ramp out, but we get about 90% contrast for only about a 4x difference in the qubit lifetime versus the photon lifetime. If you increase kappa, you can do much better. So this device, we were aiming for a high Q cavity, so it's actually bad at this.
Mati?
Yeah, thank you very much for the great talk. I have a question on the last part. You mentioned this qubit interaction. So what kind of, do you have some intuition to that? I mean, earlier in this today we have heard these talks where you have like all-to-all coupling or changing signs randomly between the qubits. And here with transmos you can also change the frequency. So if I want to couple two transmons here somehow in the lattice, how would you do in this setup?
Yeah, and so the intuition that I have is that the dispersive bands in, the quadratic band edges are going to give you an exponentially localized interaction. The flat band gives you actually a very short range but frustrated magnetic interaction. And that's the very simple picture if you have sort of a nice hierarchy of scales that you can go near one band and couple to it, but sort of not couple to the others. This particular device does not have such a clean separation. To be brutally frank, there was a manufacturing error and the hopping is half what it was supposed to be and the G is twice what it was supposed to be. And so we never couple cleanly to one band in particular. But we could fix that in a later generation. Also, these 3 qubits are in a line, and so we would never see the frustration effects. And so what we've really been concentrating on is developing the measurement tools that we would need to go back and do this in a more fine-tuned realization or in the hyperbolic case. I think that's where we're hoping to go next, but I didn't want to dive straight into that unknown pool first.
All right, thank you.
Connected to that, like the flat band that you engineer is topologically trivial or not?
It is trivial.
It is trivial.
It's very much like the one in the Kagome lattice that you have plus and minus, and it.
So the compact localized states are orthogonal, or like expanding.
Now, because it's a little bit, it's less trivial than the Kagome lattice because the underlying lattice is non-bipartite. And so in the Kagome lattice, everything is really localized to one plaquette. And here they are localized more like to pairs. And so there's a bit more interlocking, but it is not going to give you what you would get from a more exciting flat band that has a Chern number or something like you might get from twisting where you have some power law fractal modes. There might be ways to do that in this kind of a system, but this doesn't have it. And then James had a question behind you.
Yeah, just quickly. So in this model, is this Hamiltonian being written in the lab frame, or is this in the frame of the coupling?
This is in the rotating frame.
Okay, in the rotating frame.
Yes, that is very critical for this. And so that allows us to get the cavity energy down on a comparable scale. And so it's in the rotating frame of the qubit of the drive, yes.
Of the drive. And then the cavity is tuned exactly onto resonance with the bare qubit transition frequency, or is it like red detuned or blue detuned?
And
or
so,
like where's the cavity in all this?
The cavity is here, the qubit is here, and then the qubit has a Zeeman splitting. And so so this lowest data here is for both of the Zeeman states, well below the cavity. This one is when you get within about a G of the cavity. And this is 2G and this one is G, so it's a little bit closer. For reference, we go with about an 80 megahertz field here. So we have an 80 megahertz Rabi rate at the peak. And so there's one of these modes can be about 80 megahertz below the cavity and the other one about 10 below, that kind of thing.
Thank you.
I will take the
same mic. Yeah. Great results, nice talk. I also had a question about the Floquet cooling. So how much fine tuning is there here? Like, what's the condition on the cavity kappa? Is it just a resolved sideband condition, or is there something more going on?
Okay, so to get a reasonable contrast, you want your photon decay to be faster than your qubit decay by some relatively appreciable number. Sure. And then the other thing that we really need is for the Zeeman splitting to be big compared to G. Because what you're relying on is that one of these modes hybridizes well with the cavity and the other one doesn't. You need differential per cell. And so we have about...
So is it G compared to B naught or like kappa compared to... Like I only want to see only one of those Floquet states should see the cavity density of states? Or is it more complicated
and so
than that?
I believe that when Anusha was looking at the numerics, you get the best stabilization for about G equals kappa, but you need the Zeeman energy to be large compared to G, otherwise you'll just percell both of them. Okay. Because if you imagine that G is much larger than the Zeeman splitting, then both states will hybridize with the cavity, and you won't get preferential loss from one of them. But it works pretty well, right? So this is for one of the states detuned by 2G and the other one detuned by about 10G. And we're getting appreciable contrast already here. And our photon lifetime is 2 microseconds, our qubit lifetime is 10. So actually, even for that very modest splitting, as long as you get a third mixing with the cavity, it works. And so if we'd gone back and made this a lossy cavity, this would work really well for a fairly wide range of things. You could also imagine, instead of using a cavity, using something like a bandpass filter so that everything in some range is per cell sort of suppressed. And so then you might be able to clear out a bunch of excited states instead of just this very, very simple two-state model.
Yeah, and that was a related question. So you could imagine doing this for in principle, for some many-body state that was Floquet-driven.
And so I think Anusha is working on that right now. What we have been able to do, and I really don't have time to explain it, but we were intending to make a topological photon pump when we did this. So we took qubit in a cavity in a rotating field. That's why we made a high Q cavity. But that pump is limited by diabatic processes and loss in the qubit. And so what David Long, Anusha's student, was able to cook up is a 2-cavity model where you're pumping with a high Q cavity, and then in part of your cycle, you come into this Zeeman resonance with the low Q cavity, and the low Q cavity cleans up the errors in the qubit so that when you go back to pump through the good cavity, it actually works. And that makes a dramatic improvement on the pumping of that. So that's at least a more complicated, you're stabilizing a qubit cavity together as opposed to just a single 2-level system.
Cool.
Okay, so in the interest of time, I think let's thank Alicia again.